So now we're going to see how we can combine different hypotheses into an ensemble of hypotheses, and in order to mitigate the effects either of bias or of variance. So we can try to attack bias or variance in this way. So these are ensemble methods, and the idea here is not to give you a very extensive overview of ensemble methods, because there are many different examples, but I'm going to focus on two examples, bagging and boosting, just to show you one way of attacking the problem of having high bias and low variance, or high variance and low bias. But then there are many different detailed approaches for ensemble methods. We are not going to cover those. Okay. So let's start with the general idea here, is that we want to combine groups of hypotheses. They can be classifiers or regression hypotheses, something like that, in order to improve classification. And we saw that there are two main problems with our predictions, whether classification or regression, which is the inability of the model to adjust to the data. This gives us high bias, or the model adjusts too much and gives us high variance. So the idea of ensemble methods is to attack one of these problems in some particular way. And we're going to see bootstrap aggregating. This is bagging. We use bootstrapping to train the model in different samples, get a large number of hypotheses, and then we combine the predictions, for example, by average or majority vote, in order to reduce variance. So this is good for models that have low bias and high variance, and we can combine them in this way and reduce variance without sacrificing bias. Boosting is training a linear combination of weak classifiers. So general, they have high bias, and we use that linear combination to reduce bias without sacrificing on the variance. So let's start with bagging. This is bootstrap aggregating, a contraction of bootstrap aggregating, because we use bootstrapping to generate a large number of replicas of our training set. This is the same trick we saw previously for computing bias and variance. And since we have a large number of replicas, we can use the same model to produce a large number of hypotheses. And now we aggregate the output of the hypothesis. This is a typo. This should be hypothesis, not models. We train the model once per replica. We get a large number of hypotheses, and then we aggregate them. Let's see an example here for regression. We have this data set. We can resample from this data set by bootstrapping and obtain a large number of samples. So this would be the bootstrap function that we use. We get a large number of replicas by bootstrapping from this data set. So basically what we get here, since we are sampling with reposition, some of these points may come repeated, and some of these points may be omitted from each of the replicas. So the replicas will be slightly different in that sense. And now we train, we fit our model, a polynomial of some particular degree. We fit our model to each of the replicas, and now we store all these hypotheses. So we add all the predictions, or if we want to store a classifier, we need to actually store all the coefficients for these polynomials. And then what we do for predicting our regression would be the average of all these predictions. So in this case, I created here a set of values just to draw the line. I average all the predictions, and here you can see each individual hypothesis drawn in gray. So as you can see, as we sample from our training set, we get different sets of points, and since we are using a polynomial with a high degree, we get a large variance between the different predictions. But when we average the predictions, we reduce the variance, because we are averaging all those predictions. The dispersal becomes a lot narrower, but we don't sacrifice the ability of the model to adjust to the data. That one is still there, so we don't increase bias in this way. Okay? So we can solve the problem. There is a variant of bagging which is called bragging, where we use the median instead of the mean. This is the one I drew here in blue. This has the advantage of being less sensitive to outliers. The median is the value which splits the set in half. So if you sort all the values, the one that is in the middle will be the median. And if you have one outlier that is very large, it doesn't make a difference for the median. Whereas for the mean, if you have outliers, then the mean can be changed. So usually median is more robust than the mean. But either way, this is a good way of using a model that has high variance and low bias and reducing the variance by averaging the result of the model. We can do this for classification too. If we take, instead of simply an average like this, it's like a majority vote. We can also use the average or do any of those computations, but we are taking the majority vote of a set of classifiers trained with bootstrapping. So in this case, with a support vector machine, I'm using the same hyperparameters for all the classifiers I'm creating, but I'm creating one classifier for each replica. And I train this support vector machine for each replica, and I have this list where I store all of them. So this is the drawback of this approach, is that you have to train a large number of instances of your model, a large number of hypotheses, and you have to keep them all, because then when we want to classify a new point, we need to look at all the classifications of all those hypotheses and take the majority vote for the final classification. So this is what I'm doing here, fitting each support vector machine to a different replica of the training set, keeping all those support vector machines, and then the prediction, I just, in this case, since we have classes of 0 or 1, we can just compute the mean of the predictions and round to 0 or 1. If you have classes of -1 and 1, you can compute the mean and then take the sign of the mean. If it's positive, it's +1. If it's negative, it's -1. So depending on how your class labels are, what we want to do here is always a majority vote. So this is the result of all the different support vector machines we are creating. You see that support vector machines are actually more robust than some other classifiers. So you don't see a very large difference when we do bootstrapping here. But still, there is some variation here between them. And when we compute the majority vote, we get that discriminant there. So that is the discriminant of the ensemble of all those support vector machines by picking the majority vote for each point. So this is one way of joining together a set of regressions or classifiers, and by using the average of the predictions, we can reduce variance without increasing bias. This works particularly well if we have classifiers that are independent, because when you take a majority vote, even a modest classifier that would only hit, for example, 60% of the time, which is this blue line here, if you average the vote of 20 of them, you get nearly 80% right. If you average, for example, 80 of them, then you're already in 95% or something like that. So if the classifiers, even if they're not very good, when you take a majority vote, it can be much better, as long as they are independent, because this assumes that the classifiers are all completely independent and uncorrelated with each other. Because, as you can imagine, if you take 20 classifiers that are exactly the same, then the majority vote will not improve anything, because they all vote exactly the same and it makes no difference. So this is especially good when you have unstable classifiers which can vary a lot with the data. So by bootstrapping, you get lots of independent hypotheses. Okay? So if you have these unstable algorithms, bagging is a good idea. Unstable algorithms with high variance, you can profit a lot by just taking a number of hypotheses and averaging them. Yeah. Unstable algorithms are those that are very dependent on the training data. For example, with support vector machines, you don't get a big gain by using ensemble methods. This would be the opposite of what I showed previously, because since supported vector machines are maximum margin classifiers, they already try to reduce that instability and too much dependency on the data. If you use a polynomial with a high degree, then you get a very unstable in this case. A polynomial with high degree would be a very unstable model, because differences in the training data can lead to huge differences in the output. Okay, so the more unstable models tend to be more uncorrelated to each other when you use different replicas, and so they approximate this ideal curve where you average the votes of a large number of them, and then you improve a lot the results. This is the ideal if there is no correlation between one vote and the next, because if they are correlated, then you get less than this gain. At the limit, if they all were exactly the same and voted exactly the same, you would not gain anything by having bagging, by having an ensemble method, because then you're averaging all equal votes, and so you get exactly the same thing as one of them. Okay, so the more unstable they are, the more they vary between the different replicas, and the more you gain by combining them with this approach. Okay? So this is bagging. Bootstrap aggregating is good for high variance, low bias models, where you take an average and we reduce the variance by taking the average. Now let's look at the other extreme with boosting, which is when you have a weak classifier. Weak classifier is one that performs poorly. You get little over 50% accuracy, for example. It's not a very good classifier. But that would be each of the base classifiers. The error is below 0.5, but it need not be much below 0.5. And the idea of boosting is to combine these classifiers, so have a linear combination of classifiers with different weights for different classifiers, in order to improve classification. So the algorithm goes like this. We are not doing bootstrapping, we are not resampling our training set. Our training set is always the same, but we are changing the weights the different examples have in our loss function. So we initialize the weights to the same value. They can be 1 or they can be 1 over n, so that we can keep it normalized. But the weights start, the examples all start having the same weight. And now we feed one classifier by minimizing our loss function with the weight. So this indicator function is 0 or 1 whether we get the right value or not. This basically is the function that indicates that we made a mistake. If our prediction is different from the target value, then it's 1. If it's the same, it's 0. But for each example, we multiply by the weight for that example. So this would be the total error that we have, but weighted by the example. And now, when we have this weighted error, so if we keep the sum of the weights equal to 1 over n, we don't need this part. Otherwise, we need this to normalize the error to between 0 and 1. But this would be the weighted error over all our data set. This is the average weighted error for all the points. Yes?
How do you change the weight of each example?
Are you talking about the algorithm or how you do it in scikit-learn?
No, how do we work?
Okay, that's the second, this slide. So this is you compute the error, and now to update the weight, you have this formula which depends on whether they are wrong or not. So basically, this is e raised to the alpha. The alpha is a function of the weight. It will be larger, a function of the error. It will be larger for larger error. And this gives you an update on the weights, which will increase the weight if the point has a mistaken classification. So points where you are making an error at present, you increase the weight. Points where the error is correct, you don't change the weight, but when you normalize here, then effectively, if you keep the sum of the weights constant, then when you increase some, the others will reduce when you normalize everything. So basically, the update rule here is that we compute this error given the different weights of the examples. Then with this, we compute this alpha value, which is how much the classifier will weigh on the final combination of classifiers. And this is larger for smaller error values, so it's the logarithm of 1 minus the error divided by the error. This means that if the classifier has a smaller error, it will weigh more on the final combination. If it makes too many errors, it will weigh less on the final combination. And now we update the weight of the examples as a function of whether or not they are mistakes. So we increase the weights of those that are mistaken, and proportional to this weight of the classifier, this alpha value. So classifiers that make fewer mistakes will increase a lot those points. Classifiers that make a lot of mistakes will not increase so much the weight of the wrong example. And so in the end, we store all these weak classifiers, and in the end, we classify by applying each classifier to one example that we want to classify. We get the results, the classification of each classifier. We multiply each of them by the weight alpha we computed for that classifier, and we get this linear combination of the different classifications. If the classes are 0, 1, or 1, then we just need to look at the sign at the end. If the classes are, if the classes are minus 1 or 1, then we just need to look at the sign. If they are 0, 1, we need to see where if they are the average of this is above 0.5 or below. This now depends on how we set the class labels, but assuming that we have class labels of 0 and 1, this weighted sum of all the votes, we just look at the sign, and this is the final classification. So let's see how this works with a specific example. We're going to use boosting with decision trees that have only one level. So if you imagine a tree that is cut, that's called the stump. So we're going to use stumps, which is a decision tree with only one level, and boosting with those trees is called stumping. But I'm just going to do here a small parenthesis to explain what are decision trees. This is a simple algorithm, and the idea is that you have a training set with 2 classes, for example, and you need to split it into 2 subsets in a way that maximizes the purity of the sets. That means that ideally you want one class to go into one subset and the other to the other. But the way the splits are made are by choosing one feature and then cutting. For example, if it's a continuous feature, we cut on some threshold value. If it's a discrete feature, we separate by the different values. So this is the general algorithm of the decision tree. Pick one feature, split according to one splitting criteria, for example, a threshold, and then you have 2 subsets. For each of these subsets, if the subset contains only elements of one class, then that is done. You don't need to do further splitting. If it still has a mixture of elements from different classes, you keep splitting. And the way to split this is the way that maximizes information gain. So there are different ways of measuring. Basically, the information gain is how much we're going from the parent set to the 2 subsets, we increase the purity, the separation between the classes. And this can be measured, for example, by classification error. Suppose that in each subset, you classify all of those as the majority class in that subset. So if you have 90 of class 1 and 20 of class 0, you classify them all as class 0, but now you made 20 mistakes there, and you compute the percentage of mistakes in that set. So if you use classification error, you can split trying to minimize the classification error into each subset. You can also use the Gini index. So this is basically a measure of how the mixture of the classes. This would be the probability of each class, or the fraction of each class there. And you sum everything, and you do 1 minus the probability squared. So you can imagine that if one of the class has a probability of 1 because it's all there, and the others are all 0, then the Gini index will be 0. If you have a mixture of classes, then the Gini index can be 0.5, something like that. So you want to try to minimize the Gini index of the subset. The same thing for the information entropy and so on. There are different measures, but the idea is always to try to measure how mixed things are in each subset. If they are completely separated, then that's ideal. If they are mixed, you want to mix them as little as possible. And now you keep doing this until either you reach a target number of levels in the tree, or you have only sets with one class of examples in each set. So let's see, for example, this data set here. We create a decision tree. We have 90 examples, so 45 red, 45 blue. This is the original set, and the algorithm chose feature 0, which is the horizontal axis here, and to separate in minus 0.8 something. So basically around here. So it's separating this set, which has 25 red examples, and this now is a pure set. There's no need to split this further, but now here we have a mixture of red and blue when you take this part. And now we need to separate again. It's going to choose feature 1, which is here in vertical, somewhere around here, and this is going to split into one set which is mostly blue, only has one red example there, so it's easy to separate, and then split in the other that is mostly red, but it keeps splitting, and in the end we get something like this. So this would be a decision tree with as many levels as needed to completely separate the training set.
But for previously to do that, we need to know previously where are the ones and the rest.
Yes, this is the training set. So you give the training set to the tree, and it doesn't mean that it will perform well outside this training set, because it may be overfitting things quite a bit when it decides to cut exactly here on the red ones or something like that. So this is, if you have a complex set of data, you can have a decision tree that has many levels, because it will keep splitting the subsets until it finds sets that only have one class. So this can easily overfit if you have a tree that is very large. But what we're going to do here with stamping, which is a specific instance of boosting, is to just use level 1 decision trees. So imagine that this decision tree stops here. It was only the first choice, and it only cut here the two classes. So this is a very weak classifier that will result in a lot of error, and it's a very simple classifier. It only does one split. And that's what we're going to use for stamping. So we're going to use this decision tree classifier. When we fit the decision tree classifier, we're going to create a classifier with this argument, max depth 1. So you only want the first decision. We don't want it to be a complex classifier, just the stamp. And we're going to fit it to the data. But one reason I chose this decision tree is that with the decision tree it's very easy to add weights to the examples. But notice that all these measures of how pure each set is can have different weights for different examples, and some examples count more than others. So with the decision tree classifier you have this argument for the sample weight, where you can just put a vector of weights for all your training examples, and you can keep adjusting that vector. So now this is simply the implementation of the algorithm. We're going to compute all the predictions for our training set. All the errors are those that do not correspond to the prediction. So we get the index of all the errors here. And now we're going to compute this expression here to update the weights of the errors. So everything that has a 0 there will have e raised to 0, which is 1, and the weights multiplied by 1 will not change. So this only changes the weights of those points that have mistaken classification. So we're going to do that. We're going to update, compute the alpha, compute the new weights, and normalize the weights. So we keep it so that the sum of the weights is always 1, so that we don't have to include this term here when computing the error. We keep the weights normalized. But this is just all the steps of the algorithm, and we keep appending the stumps that we trained, the decision trees, and the corresponding alpha that we computed based on the error. And this will be our final classifier. Will be a list of decision trees that have been trained with different weights for the examples, and a list of the respective weights in the final combination. So this is what's happening. The first stump makes this decision, so this is basically the same as happened here, but we are pruning the tree on the first level. So the first stump will only split our data this way. All these points are correctly classified, all these blue points are correctly classified, but these red points are wrong. So their weight increases. Then in the second iteration, we again compute just a decision tree with one level, but now these points count for more. So now the tree will not cut here, because then it will have a bigger error because those points count for more. It will cut over here. And now these points are correctly classified, so they will shrink when we normalize the weight, but these are wrong and the weight will increase. And now we keep doing this. And as we keep doing these classifications, some points will be incorrectly classified, the weights will increase, the others will keep decreasing, and this is the result of the combination of all the classifiers as we keep accumulating them. And as you can see, we get something that manages to classify everything correctly by using the classification of each stump. Remember that each stump only does a horizontal or vertical split because it's only one decision, but each stump has a different alpha, and in the end all those different combinations with the different weights will give us the final classifier. So this is something this is an example of boosting with decision stumps, and it works the opposite way of bagging, in the sense that instead of taking a model that has a very large variance and very large power to adjust to the data, it goes the other way. It takes a model that is very simple and cannot classify very well the data, but now it creates a linear combination of those in order to improve classification. So now, for classifying data, we have all the hypotheses that we kept, all the stumps here, and if we want to classify a new example, then we simply add the predictions of each hypothesis multiplied by the weight of that hypothesis in our final classifier. And now we get the net prediction, which is the product of those classifications in the weight, and we can use the sign function or just go to -1 or 1 depending on whether the overall result is positive or negative. So remember that the final classifier is not any particular one of these stumps, but it's the linear combination of all of them that we train. Okay? So another way of looking at AdaBoost, I'm going to go through this briefly, but if you want you can look at this derivation in Bishop's book, is if we imagine that we are using an exponential loss function. So basically this is e raised to minus the product of the target and the classification. If the classes are -1 and 1, the target and classification, if they have the same sign, this will be positive, but there is the minus there, it becomes negative. So if the function that's doing the prediction has the same sign as the target class, then this will shrink to 0. But if not, if the function that is doing the prediction has the opposite side, then this grows exponentially the more the error is there. So you can imagine that this is the error function that we're trying to minimize, and the classifier that we are using here is a linear combination of the base classifiers. So it's a set of basic predictions, each one multiplied by the alpha. So if we want to do this minimization, this would be very complex because we are trying to minimize a large set of classifiers, but we can specify and do this as a sequential minimization. So when we have m classifiers, we are only minimizing the last one, and we assume the others have already been adjusted and they are fixed. So we start with the first one, then when we go to the second, we assume that the first one is fixed, and so on, and we do the minimization sequentially. If we do it this way, then we can, the minimization, we can consider only the last classifier, the others are constant, and we can decompose this into the error contribution of those points that are correctly classified and those that are incorrectly classified. And as we minimize only with respect to the last prediction, we get this cost function, which is the same as we used for other boosts, and minimizing with respect to the alphas here, the coefficients that multiply each individual classifier, then we get the same expression we got for other boosts. So basically you can think of boosting this boosting algorithm as trying to optimize the set of classifiers, so minimizing that exponential error function for the complete set of classifiers, but doing it sequentially. We start by minimizing the error for the first one, then we take the first one as constant and we do the second, the third, and so forth. So this leads us to that original algorithm. Now, you can use boosting for any classifier that has at least 50% accuracy that you require for the computation of the error and so on, but that should be simple because lower than 50% it's like you're doing mistakes on purpose, and you need to be able to adjust the weight of your training data. So in practice that would be the limiting factor, because you need a simple way of adjusting the weights in order for the algorithm to work. Okay? So boosting, you compute a linear combination of weak classifiers by adjusting the weight when you train the weights of the examples when you train each hypothesis. This is what makes each hypothesis different. You're always using the same data set but with different weights. For bagging, you average predictions of a large number of hypotheses, but those hypotheses are different because you're training with different data sets obtained with the bootstrap aggregation on the original training data. Okay? So obtained with bootstrapping. That's why it's called bootstrap aggregation in this algorithm. So bagging is good for models with low bias and high variance. Note that if you have a model with a high bias, it makes no sense averaging the results because the bias is already the average error. So if you average different hypotheses, you still have a large average error. So it's good for models with low bias but high variance, and you reduce variance by averaging. Boosting is good for models that are simple and have high bias, and so basically that are underfitting, because now you're creating a linear combination of these models that can be more powerful than the individual models. So this is the subject matter for the first test. The first test will be in about 3 weeks, I think, or 2 weeks? 3 weeks, I think. Yeah, it's the 6th of November. But this is the subject matter for the first test. This year, the first test is a bit later than usual, or we started sooner than usual, I'm not sure. But these first 12 lectures cover the subject matter for the first test. The next 2 sessions, so until lecture 16, will not be on the first test. Those will be on the second test. And then during the week of the test, so there will be a session in the day before the test. That one will not have new subject matter. It will only be for revisions and questions that you have. Okay? So that one, I will not record that session, and it will only be for your questions and whatever you want to look back on. Yes?
Does the model for this year test will be similar to the previous year?
Yes, you can check the test from the previous years. My imagination is rather limited, so I guess it will be mostly the same. So you can bring one handwritten A4 sheet on both sides, but it must be identified and your own. So you cannot share the sheets. Each person uses their own. Remember that the exam, if you are thinking of doing this course in the exam I will score 2 halves independently, and you still retain the grade of the test. So even if you don't want to come to the second test, it may pay to come to the first one and do the exam only for the second test or whatever. In addition, the test will include questions for the assignment. So even if you don't want to do the test, come anyway and write in the questions for the assignment. Then you can leave after half an hour or something, but those will be part of your assignment grade. So there will be some questions for the practical part. Okay. So to sum up this part, we saw bagging and boosting, different ways of attacking the bias variance problem, bagging for reducing variance by averaging, and boosting to reduce bias by combining different classifiers. So you have, for example, in Bishop, you have a more detailed derivation of ADA boost, and you have these covered also in these books.